In this video, we give some alternative definitions of rectifiability that may be more convenient depending on the circumstance. So given a subset E of Euclidean space of positive and finite m-dimensional measure, then the set is m-rectifiable if and only if it can be exhausted up to a set of m-dimensional measure 0 by a countable union of sets gamma I, where the gamma I are either of the following forms. So they can be Lipschitz images of subsets of Rm. They can be bi-Lipschitz images of subsets of Rm, or they can be just bi-Lipschitz images of Rm. And finally, they can be copies of m-dimensional Lipschitz graphs. Okay, so why is such a theorem important? Well, in some circumstances, it may be easier to verify one of these properties than another. So for example, notice that property A is weaker than is a priori weaker than the definition of being rectifiable, which originally stipulated that you had to be covered by countable unions of Lipschitz images of Rm, not just subset. And then we've also seen when studying cone points that it is sometimes easier to establish rectifiability by showing that a set can be covered by a countable union of Lipschitz graphs. Now, what we'll see later is that the reverse direction is also very useful. That is to say, given a set that is rectifiable, it is helpful to know that it is covered by better sets than just Lipschitz images of Rn. So for example, C is a strong property to have. So if you're rectifiable, not only are you covered by Lipschitz images of Euclidean space, you are covered by bi-Lipschitz images of Euclidean space. Or even better, you're covered by m-dimensional Lipschitz graphs. Okay, so let's show some details about how to prove this result. So first of all, m-rectifiability is implied by the first one and Kirsch-Braun's extension theorem. Right? Because if you have a Lipschitz map defined on a subset of Euclidean space, you can extend it to a Lipschitz map on the whole Euclidean space. So A implies rectifiability quite immediately. Secondly, B trivially implies A, just because any bi-Lipschitz map is also Lipschitz. C implies B, naturally, just because we can pick these sets AI just to be Rm. And finally, D implies C, because recall that if gamma I is a Lipschitz graph, if we can write it of the form gamma I is equal to f of Rm, where big F of x is of the form x plus little f of x, where f is a map from some plane in some m-dimensional plane to V perp, okay? And then what you can show actually is that and so f is Lipschitz, okay? So what you can show is that if f is Lipschitz, then this function big F of x is actually bi-Lipschitz. So Lipschitz graphs are always bi-Lipschitz images, okay? So what we'll do in this video is focus on the last implication to complete this chain of implications. So we'll show that m-rectifiability implies that my set can be covered up to a set of measure 0 by countably many Lipschitz graphs. So our goal now is to show that any m-rectifiable set E can be covered up to a set of Hausdorff m-dimensional 0 by Lipschitz graphs. So without loss of generality, we can actually assume that E is exactly equal to the one Lipschitz image of Rm. And the reason why is because any rectifiable set is a countable union of Lipschitz images of Rm. And so if we show that any one of those Lipschitz images can be covered by a countable union of Lipschitz graphs up to a set of measure 0, then that will imply that the whole rectifiable set E can also be covered by Lipschitz graphs up to a set of measure 0. So again, we'll assume that E is just the Lipschitz image of Rm for some Lipschitz map F. Now, recall the Lipschitz decomposition theorem tells us that we can find disjoint subsets E1, E2, etc. in the domain of F, so that F restricted to any one of these sets is an Li by Lipschitz function for some constant Li. And moreover, the images of these sets, which we'll call Gi, cover almost all of this image of F, that is to say, almost all of the set E. So our goal now is to show that each one of these images, so each one of these sets GI, it can be covered by a countable union of Lipschitz graphs up to a set of m-dimensional measure 0. So let's fix one of these sets GI. So Rademacher's theorem tells us that the derivative of F exists at almost every point in the domain of F. So in particular, for almost every point in the set EI. So that implies that for any epsilon that we specify, we can find some number Rx, so that for R strictly less than Rx, this inequality is satisfied. So recall that this function here is the linear approximation to F at the point X. So this says that the difference between f of y and its linear approximation is very small for values of y very close to x. So notice that if we let v be the image of this linear approximation of f, what this inequality here is saying is that for y inside this ball, the distance between f of y and an element of the plane divided by y minus x is less than epsilon over Li. So in particular, this implies this inequality right here. Okay. All right, so this is the inequality that we had from the previous slide. So V is the image of our linear approximation, and we know that for values y inside this ball, the distance between f of y to the plane V divided by y minus x is less than epsilon Li. Now, notice that since f restricted to EI is Li by Lipschitz, so this says that if we have a point Z in GI, okay, so recall GI is the image of EI, so that means that Z is actually equal to f of I for some point y inside EI. Then these inequalities have to be satisfied. So notice that, recall that Z is equal to f of y for this y. So these two inequalities right here is just restating the by Lipschitz property. Okay. So in particular, we then know that the ball center at f of x of radius r over Li intersected with gi is contained in the image of bxr under f. Okay, so why is this the case? So let's suppose that we had a point z inside this intersection. So because it's inside gi, that means that it must equal f of y for some y in ei. Okay, since gi is the image of ei. And then we can apply our above inequalities, in particular this one, to get that y minus x is at most Li times the distance between z and f of x. But by assumption, z is inside this ball, right? So the distance between z and f of x is at most r over Li, and so the Li's cancel and we just get r. So this implies that y must be inside the ball center x of radius r, and that implies that z, which is f of y, must be inside the image of this ball under f. So this containment then gives us the following. So if we look at points that are inside this ball intersected with gi, and we look at their distance to v divided by the distance from z to f of x, okay, well, this ball is contained inside the image of bxr under f, and so that means that each one of these z is actually equal to the image of some y inside bxr. So this quantity here is at most this quantity right here, where notice that we also bounded the denominator. So z minus f of x, okay, using this inequality up here, or rather this one. So z minus f of x is at least y minus x over Li. And so flipping the inequalities, we get that 1 over z minus fx is at most 1 over this quantity. Okay, and then using this inequality up here, okay, so if we ignored this L of I, this inequality up here says this fraction is less than epsilon over L of I. But now we're also dividing by Li in the denominator, so that gives us that this is less than epsilon. So now I claim that this inequality here implies that f of x is a cone point for gi. Okay, so why is this? So let's suppose I have a point f of x inside gi, and let's say this plane here is the m-dimensional plane V. Okay, so this inequality tells me that for points z inside this ball center at x, that are also in gi, their distance to the plane is a lot closer than their distance to f of x. So in particular, it's epsilon times their distance to f of x, which means that the set G is going to be trapped between sort of these two lines here, where the angle of these lines is something comparable to epsilon. And the set G lies within these wedges. Okay, so GI. So in particular, if you look at the sort of area outside these wedges, okay, then that area is going to be a cone that does not intersect your set GI. And therefore, the point f of x is a cone point for GI. And thus, almost every point in GI is a cone point, and therefore GI can be covered by a countable union of Lipschitz graphs, and thus any rectifiable set can. So one thing I left out of the proof is that I implicitly assumed here that this plane V was m-dimensional. Now, that might not necessarily happen if the derivative doesn't have full rank. V could be a m-1 dimensional plane, for example. But we can assume, without loss of generality, that the points we consider are points where the derivative has full rank by Sard's theorem, since the images of these points will exhaust almost all of the image of a Lipschitz function. So that completes the proof that any rectifiable set can be covered up to set of measure 0 by countable union of Lipschitz graphs.